Ladies and gentlemen of BlueHat 2025, trust nothing.
Hello, everyone. It's great to be here today. I'm very excited. We have quite a challenge together today. Toughest slot of the day right after lunch. I bet that some of you are feeling kind of dizzy, falling back in their chairs. So I believe in us. I'll try to do my best to help you stay awake. So before we get into the talk itself, I wanted to start with a little apology. In case any of you came here thinking we're going to be covering the latest developments of Visual Basic malware, I'm sorry, we're not going to be covering this VBS, but rather the other VBS. So absolutely no Visual Basic script today. We're going to be covering Virtualization Based Security. Sorry for any misunderstandings. My name is Ori David. I'm a security researcher at Akamai. My background is in red teaming and threat hunting. And today I cover a wide variety of research topics in the Akamai security research team. And today, as I just said, we're going to be covering VBS, Virtualization Based Security, one of the most interesting security advancements in the world of endpoints in recent years. After covering the basics of VBS, we will get into our main topic, which are VBS Enclaves, a security feature that is enabled through VBS. So we will understand what is it all about and how we can utilize it. And then we'll get to the fun part, abusing VBS Enclaves. We will see how attackers can take this security feature and do some pretty interesting malicious things with it. OK, so let's start with Virtualization-Based Security, VBS. It all starts with security boundaries. So traditionally, operating systems in general, and Microsoft as well, relied on processor rings as their security boundary in order to protect the operating system. The idea was we can use ring 0 to run the kernel, ring 3 to run user mode application, and this separation will allow us to protect the operating system from user applications and from exploitation. Now, this proved to be insufficient over time as an actual security boundary. Microsoft doesn't even consider it an admissible security boundary today, because attackers can bypass it pretty easily today. So we see a lot of kernel exploits. The kernel exposes a very significant attack surface, so attackers continue to find ways to get in there. And of course, bring your own vulnerable driver. You don't even need to target Microsoft's code when you can target any one of the tens of thousands of drivers, third-party drivers, find a vulnerability in them, and yeah, you're in the kernel again. So processor rings were simply not enough to protect the operating system from malware. And this is where VBS came into the picture. So let's first understand how it got into our life. And its origin came through Hyper-V. Hyper-V, Microsoft's hypervisor, which was originally used to run virtual machines, either locally or in the cloud, in the case of Azure. And one of the most important things that a good hypervisor has to do is isolation. In particular, memory isolation. We would never want to allow a situation where one virtual machine can access the memory of another virtual machine, obviously. So yeah, again, Hyper-V is it manages the virtual machines, it can enforce this isolation between them. So someone at Microsoft had the good idea at some point to take this same principle and apply it to the operating system itself. So if before we isolated different virtual machines, now what we can do is we can execute our operating system on top of Hyper-V. And by doing that, we can use, again, the same memory isolation technique in order to isolate memory within the operating system from the operating system itself. This is the basic idea of VBS. We use it to implement what is called virtual trust levels, a new set of security boundaries that we can apply on the operating system. So if up until now we had two execution modes, ring 3 user mode, ring 0 kernel mode, now we have when we introduce VTLs, additional security boundaries and additional execution modes are introduced. So first we have VTL 0. This is the least privileged virtual trust level, and it executes the normal world, the normal execution modes that we know and love, user mode and kernel mode. Now, things get interesting when we introduced VTL 1. VTL 1 is a more privileged virtual trust level than VTL 0. And this privilege comes into effect in the form of memory isolation. The idea is that code running within VTL 0 cannot access memory within VTL 1. But on the other hand, VTL 1 can touch the memory of VTL 0. So this is how, in a nutshell, it makes it more privileged. This new separation creates two additional execution modes. First, we have VTL 1 ring 0, which is the secure kernel mode. This is a more privileged kernel, which can actually enforce policies on the normal kernel. On top of that, we have isolated user mode. Now, this execution mode is also very interesting. On the one hand, it runs in ring 3. It is a user mode. It executes in user mode. It cannot perform sensitive kernel operations. But it still enjoys the advantage of running in VTL 1, which is, as the name suggests, isolation. Up until now, before we introduced VTLs, if an attacker were to compromise the kernel, it was pretty much game over. At this point, they could control the operating system and do whatever they want. Now, even if an attacker were to compromise the kernel, they wouldn't be able to access either secure kernel mode and isolated user mode. Nothing in VTL 1 can be accessed by VTL 0. So this is really, in a nutshell, VBS, which now brings us to our next topic, VBS Enclaves. So first, let's start with what is an enclave. And it's a bit of a weird definition at first, but stay with me. So an enclave is a region of memory within a process that the process cannot access. It cannot read from it. It cannot write from it. OK? So why would something like that be useful? So imagine a scenario where we have some sort of a secret that is handled by our process. If the process stores this secret in its normal memory, any attacker who were to compromise either the process directly through an exploit or the operating system, allowing it to gain access to the process, could then steal this secret. If we put the same secret within an enclave, because the process itself cannot touch the secret, it cannot directly access it, even if the process is compromised, our secret is kept secure. In order to utilize the secret, so it will actually be useful somehow, what we can do is invoke methods exposed by the enclave. So in this example, we cannot directly touch the key, but what we can do is, for example, request the enclave to encrypt or decrypt a certain value using the key. This way, the actual secret is never exposed, but we can still utilize it. So yeah, this is the basic idea of a VBS enclave, an inaccessible region within the process. It has many security applications. This is just one example for what we can do with it. And an enclave is a general concept. So the first implementation of enclave was actually a hardware implementation. But it turns out that VBS actually provides a very elegant solution for implementing software-based enclave. The problem with a hardware-based enclave is that if you don't use the correct processor, you can't utilize them. So here we have something that any computer that supports VBS can utilize. And the way that we do that is simply we kind of split the process in half, where one half, the normal process, would be in normal user mode, VTL 0, and the enclave will be in VTL 1, the secure isolated user mode. When we do that, again, we go back to the same point from before. Nothing in VTL 1 can touch the enclave. So even if the kernel was completely compromised, the secret that is within the enclave will remain secure. OK, so now let's get into some additional details of how enclaves are used in Windows. So first of all, any process can create an enclave. It is not a privileged operation, so any process can do it. And after creating an enclave, we can load an enclave module into it. An enclave module is a DLL that is compiled specifically for the purpose of running within an enclave, which exposes the functions that could be invoked by the process. So this is the logic, the brain of the enclave. We can simply load it into it. Once we load the DLL, we cannot touch it. We cannot even access the normal exported functions. There are only specific functions that are exported for the purpose of being called in the context of an enclave. In order to communicate with the enclave, we can use the call enclave Windows API, which enables us to trigger these methods. One final note, which is very small here, but it is going to be the next 20 minutes of our talk, is that we can't just load any arbitrary DLL into an enclave. Microsoft aims to protect isolated user mode, and it doesn't wish to allow any code to execute within it, kind of with a similar idea to the kernel. So yeah, just like we need to sign drivers in order to load them to the kernel, we need to sign enclave modules in order to run them within an enclave. Yeah, so this was VBS Enclaves, which now leads us to the fun part, abusing them. So the little small caveat, which I just mentioned, we're going to tackle it in the next section of the talk. The motivation for how attackers would want to abuse enclaves is pretty clear. So the concept of running malware within an enclave can be very interesting. We have two main advantages. So the first one is that we are operating within a memory region which is inaccessible. If we load our code into VTL1, nothing that runs in VTL0 can access it. This includes EDRs, security analysts, and a lot of other things that malware would want to avoid. So let's say we load shellcode into an enclave, an EDR cannot scan this shellcode. The second advantage has to do with the behavior of enclaves. So not only we get this advantage that our memory cannot be touched, but actually analyzing our behavior becomes much harder because of the way enclaves call APIs. When a normal process invokes a Windows API, it goes through the normal process of going through Windows DLLs, a series of Windows DLLs, eventually finding its way to the kernel through a syscall. An EDR, which runs here, can have a lot of fun because they can hook the DLLs to detect suspicious behavior. They can monitor our activity in the kernel. Again, a lot of detection opportunities for EDRs. On the other hand, if we trigger a Windows API from an enclave, well, we no longer go through the normal Windows DLLs, but rather we go through a separate set of VTL1 resident DLLs. So for example, we won't use anti-DLL, we use VERT-DLL, which is VBS Enclave runtime DLL. And from there, we go to the secure kernel, not the normal one. Now, the beautiful thing is that an EDR cannot touch this process as well. It cannot hook the DLLs, it cannot access the secure kernel. So again, not only is our memory protected, but our behavior is also going to become very hard to analyze. Okay, so yeah, sounds interesting, sounds cool, but as I just said, we need to sign enclaves in order to execute them. We can't just load any piece of code that we want. So in the next section of the talk, we will cover a few solutions that could allow attackers to actually get their code to run within an enclave. We'll start with legitimate signatures, we'll go to loader vulnerabilities, and we will then cover debuggable enclaves, and finally, bring your own vulnerable enclave. So right out of the gate, the most straightforward solution would be to legitimately sign the enclave. We have seen attackers do things like this in the past for drivers and other executables, where they were able to obtain a legitimate signature, either by compromising a third party which is authorized to sign, or by creating a shell company and getting privileges for signing themselves. This solution would probably only apply to advanced nation states, but it is still something that we can consider as an option. Next would be to exploit a vulnerability in the loader of the enclave, in the loading process of the enclave. So when the secure kernel, when we load an enclave, the secure kernel is in charge of validating its signature. In theory, we could identify a vulnerability in this process, which is what Alex Ionescu did a few months ago. And in theory, this vulnerability could allow loading unsigned DLLs into the enclave. So yeah, while this specific vulnerability was fixed, advanced attackers could potentially identify additional vulnerabilities like this, enabling them to load their code into an enclave. So both of these options are valid, but they also sound pretty hard. So I wanted to explore additional options that would be a bit easier. So I came up with two ideas of what attackers can do to get their code to run within an enclave. And the first idea was abusing debuggable enclave modules. OK, so when you try to develop an enclave, you might come into a bit of a problem when doing it. It turns out that debugging enclaves is not really straightforward. So the entire idea of enclaves is that nothing within VTL0 can touch their memory. You know what runs in VTL0? Your debugger. So if you simply try to debug an enclave, you won't be able to access its memory, to read it. You won't be able to place breakpoints. So yeah, that's a problem. And because of this, Microsoft created debuggable enclaves. And the idea is that while compiling an enclave module, you can specify a flag that will make it debuggable. And when you do that, you can now load the enclave, and magically, your debugger now works. You can access the memory, you can place breakpoints. A lot of fun, I really recommend. So yeah, when I saw this, I was kind of confused, because the entire idea behind enclaves is that, well, nothing in VTL0 can access their memory. And here we are seeing a VTL0 process accessing it. So yeah, could we be accessing VTL1 here? And it turns out that we are. Originally, I thought that Microsoft might have pulled a trick or something where they load the enclave into VTL0 and make it look like it's loaded into VTL1. But it's not the case. Debuggable enclaves are loaded into VTL1. What happens is that in order to enable debugging, the secure kernel implements certain exceptions that allow us to debug it. So for example, if we try to access the memory of an enclave, we will go through the skmm debug read-write memory function, which determines if the enclaves that it is being accessed to is debuggable. And if it is, the access is allowed. Similarly, we have the skmm debug protect virtual memory that allows us to change memory permissions on enclaves in case they are debuggable. So now that you understand a bit about debuggable enclaves and how they work, we can get into the interesting stuff of what we can do with them as attackers. So first, and pretty obviously, using debuggable enclaves for production applications is a really bad idea. The entire point of using an enclave is creating a memory region which cannot be accessed. When the enclave is debuggable, its memory can be accessed. Not a really good combination. And yeah, Microsoft really could not have been more clear in their documentation about this. Yeah, you shouldn't do that. If any application uses a debuggable enclave, it is completely meaningless. Anyone will be able to access the entire memory of the enclave. So this is one issue. But it turns out that there's more here. In this scenario, we were able to, if we find a specific application that uses a debuggable enclave, we can attack this application. But what if we were to obtain any debuggable enclave? It doesn't have to be tied to any specific application. So if we manage to do that, well, any process can create an enclave, as we previously mentioned. And any process can load any enclave module as long as it's signed. So we, in theory, could create this process and load the enclave into it. And then what we can do is we can debug the enclave, utilize the exceptions implemented by the secure kernel, and use that to execute code in isolated user mode. So I will now go through the kind of high-level process. If you want to see additional details, they are available in a blog post that we published on this topic. So here, the attacker obtained a debuggable enclave, loaded it, and as we can see, we have an enclave routine here, a function which is exported by the enclave. What the attacker can do is, with a series of pretty simple steps, obtain code execution. So we use getProcAddress to obtain the address of this routine. We then change its memory permissions by calling virtual protect into page execute read write. This is only possible, again, because the enclave is debuggable. We can then write shellcode overwriting the original routine. And finally, we can use call enclave to trigger this routine. At the end of this pretty simple process, we will have code execution in IUM, which is pretty nice. But if you've been paying attention, you may have already realized that there's a catch here. And the catch is that this memory access actually goes both ways. Just like we can access the enclave in order to insert our shellcode, for example, an EDR can do the same thing. The memory is no longer inaccessible. But despite that, I do still think that there are some advantages to this technique. So first, this is an unusual way to execute code. It is certainly an option that an EDR or an analyst will miss this execution, as it is abnormal. So yeah, attackers could utilize it for this reason. And also, we still do enjoy the the API evasion advantage that I previously described. Even though the EDR can touch our memory, it can still not inspect what happens within the secure kernel. So if we call APIs in VTL1, still an EDR will have a limited look into them. So yeah, this is overall a nice technique that could enable a semi-VTL1 execution, which could evade detection in some scenarios. One final caveat is that I haven't actually managed to find one yet, meaning a signed debuggable enclave. But I still think that I didn't just waste 5 minutes of your time, because I strongly believe that some will leak eventually or even very soon. Today, enclaves are kind of not really utilized, and not a lot of organizations use them. And it looks like Microsoft are pushing in this direction. They are themselves beginning to use them more and more. And I think it's only a matter of time before more developers begin to utilize them. And with more people utilizing them, someone will probably fuck up, and we will find one of them in a production build. And from there, the way to VirusTotal and to all of us is pretty short. So yeah, I still think this is an option that we should consider. OK, so now we get to our final method for today, which is exploiting vulnerable enclave modules. So the idea here follows the same principles of the bring your own vulnerable driver technique. We wanted to get code execution in the kernel. We can't load any driver, but we can load signed drivers. We load them, we exploit a known vulnerability, and we get code execution in the kernel. So the same exact idea could, in theory, be used for enclaves. We find a vulnerable enclave, we load it into IUM, and we exploit it to execute code, maybe. So I began looking for such a vulnerability, which eventually led me to CVE 2023-36880. This is a very interesting vulnerability in an enclave module that is used by Microsoft Edge. Now, while the vulnerability is classified as an information disclosure vulnerability, if you take a look at the actual notes, you will see that Microsoft also claimed that it could allow limited code execution. So it sounded pretty interesting. I decided to dig into it. This vulnerability was discovered by Alex Go, I hope that I pronounced this correctly, from the Chrome security team, which also shared the POC. The vulnerability is actually pretty simple, and it provides an arbitrary read-write primitive within the enclave. So we're not talking about a debuggable enclave like before. It is a normal signed enclave, which we shouldn't be able to access. But using this vulnerability, we can write what we want, wherever we want within the enclave, and read anything we want from the enclave. So when I found this vulnerability, I was able to obtain a file, a vulnerable file through VirusTotal, which I could then load and begin playing with. My initial idea for gaining code execution was to utilize the arbitrary read-write primitives in order to gain just that. So the high-level idea was to leak the address of the enclave stack using the read primitive and then overwriting it with a ROP chain eventually getting shellcode execution within the enclave. But after beginning to test this, I quickly encountered a problem. And that is that enclaves use ACG, arbitrary code guard, by default. So ACG is a mitigation policy that could be applied to Windows processes and the kernel as well. And what it does is it ensures that no dynamic code can be executed by the process, meaning only code that was present in the original binary of the process can be executed. If we try to, for example, allocate a new memory region for shellcode, we will fail. So yeah, it enforces two rules. We cannot create new executable pages, and we cannot turn executable pages writable. And yeah, this little mitigation kind of crushed my dreams for getting code execution. I was able to create a POC for triggering a ROP chain within the enclave, but the problem is that I couldn't find anything useful to do with this ROP chain. Again, we can't allocate new shellcode to run within the enclave, so this is probably what Microsoft meant by limited code execution. Yeah, so as of today, I didn't find a way to execute it for arbitrary code execution. Here we can see an example of allocating a read-write execute page within the enclave. This is an enclave that I've written as a demo. And you can see that we get the ACG error message that the process cannot load dynamic code. So at this point, I was kind of sad. I knew that I had something interesting here. This enclave was too interesting to be useless. And while I couldn't find a way to execute code, I knew that I could do something with it. And eventually, after a few sleepless nights, I had an idea. So this is Bring Your Own Vulnerable Enclave, round 2. I decided to try to remain positive, and instead of thinking about what I can't do, I'll try to focus on what is possible and what I can do. So the vulnerability actually provides us two very interesting capabilities. First, we can write any data that we want into VTL1. While we couldn't find a way to execute code, we could still store data there. And this on its own is pretty interesting because, again, EDRs will not be able to scan this memory. So if you wanted to hide something malicious, this could be an interesting direction to go with. And the second interesting capability is the ability to write data into VTL1 from the enclave. When we trigger the vulnerability, we can get to enclave to write data wherever we want within the normal address space of the process. This is interesting because, as we have mentioned before, an EDR cannot hook this write function, write operation. So we get this kind of a stealthy write operation that cannot be hooked by an EDR. By combining these two capabilities, I was able to create a memory evasion technique. I called it Mirage because all the cool kids name their tools. And it's a sleep obfuscation technique. A sleep obfuscation technique is a technique that tries to hide payloads by operating in a cycle. So normally, for most of the time, the payload is sleeping. It remains in a dormant state where it doesn't really do anything. And it hides from the EDR. And once in a while, it wakes up, executes its code, and then goes back to sleep. The idea that I had here was to hide the shellcode, hide the payload of Mirage during sleeping in isolated user mode, in the enclave. Other sleep obfuscation techniques do things like encrypting a shellcode or turning it non-executable. But even when they do that, it improves evasion, but at the end of the day, their payload can still be accessed. If we seal our data within an enclave, nothing can touch it. So this is a significant improvement. So the high-level idea is Mirage will first write shellcode into the enclave by exploiting the vulnerability. And here is the baseline of Mirage. For most of its time, this is what it's going to be looking like. If an EDR scans us now, it will not see anything. Now, every once in a while, based on a defined trigger or a timer, we will trigger the vulnerability again, causing the enclave to write the shellcode back into our process. We will then execute the shellcode and then trigger the vulnerability again, to write benign data overwriting the shellcode. We can repeat this cycle over and over to constantly evade detection. So let's take a look at a quick demo. So here we started Mirage, and we can see that what it does is it first loaded the vulnerable enclave, written the shellcode, and then allocated an executable buffer in VTL0. Now, allocating an executable buffer can be suspicious, but the thing is, we are never going to touch this buffer. The buffer, as you can see, now is empty. And what we will do next is we will trigger the vulnerability. And as we can see here, we placed a pause at the exact moment after the write. And we can see that the shellcode is now resident in the buffer. But again, the interesting thing is that this write operation was performed by the enclave, and EDR will not have a chance to hook it. From here, we execute the shellcode, and as soon as we finish, we have our beautiful calculator here, and as soon as we finish, we overwrite the executable memory, turning it, again, completely benign. So this is the idea of Mirage, and we can, again, repeat this process again and again to make sure that an EDR will not be able to detect us. I will quickly go again over the advantages of this technique. So first, when we are asleep, nothing can touch our memory. We cannot be scanned. And an EDR, even if it tries to detect us during the most vulnerable time, it doesn't have a hook to trigger its detection. So it will have to constantly scan the memory buffer, theoretically, in order to detect something like this. So yeah, not really practical. So this brings us to the end of the talk. The code of Mirage is found in Akamai's GitHub, so you can check it out and use it on your own. And a few closing notes. So first, VBS is cool. I hope that I might have convinced you. Not Visual Basic Script, Virtualization Based Security. And I do really think that Microsoft has done a really good job improving the protection in the world of endpoints. VBS Enclaves in particular have a lot of potential. So the thing is that other VBS usages are utilized only by the operating system itself. And enclaves are the first time that Microsoft exposes VBS to third-party developers. So I really do think that more organizations should begin to utilize them because they have a lot of advantages. And finally, I hope that I convinced you that you should probably keep an eye on them from an offensive perspective as well. As this technology becomes more widely adopted, I think that attackers will have more tools at their disposal as well. More vulnerable enclaves, maybe debuggable enclaves, maybe things that I haven't even thought about yet. So yeah, I do think you should probably keep an eye on them. If you want to read more information about this research, there's a complete area that I didn't even touch here today, which is what we can actually do when running within an enclave, which is a whole other world in and of itself. So you can check out our blog post. Yeah, and with that, thank you very much.